Our next speaker is Yonatan. Yonatan is a team lead at Wix.com Frontend Infrastructure group. There, he gets to work on developer tools daily. In his talk, Yonatan will demystify cryptography and guide us through practical applications of Node.js built-in crypto module. Please give a warm welcome for Yonatan.
Thank you. If you'll indulge me just 1 second, I need to prove to my mom that I performed on a stage in an opera. So you're all there. Great. Thank you. All right. So this is what I want to talk about today. Oh, sorry, the title of the talk is encryption, so let's hack the encryption key. Mastering Cryptography Fundamentals with Node's Crypto Module. So that's a bit of a long title, so let's try to break it down. First, what is cryptography? I'm sure you've heard the term crypto a lot recently. So crypto in Greek means hidden, and cryptography is the science or the practice of secret writing or secret communication. And as you can imagine, that plays a major role in today's system with computers. We have these networks that are connected to each other, and we want to exchange messages and hiding the message while they're being transmitted. Now, luckily, inside of Node.js, we have a built-in library for handling cryptographic operations and cryptographic algorithms. And it's a built-in module. So if you're familiar with the FS module, it means that you can get started with using it right away. You don't have to install any dependencies. It's actually based upon the widely used open source library OpenSSL. So the Node.js implementation is a wrapper around that in JavaScript. And like I mentioned, because it's one of the built-in modules, it means that it has documentation on the official site. You can go and read what are the specific APIs that are available. But in my personal experience, as someone who became interested in cryptography but was by no means an expert, I found that it's not the best place to get started because it's a very flat alphabetical list of APIs, and it has no concept of what are the things that we typically do in cryptography, what algorithm is used for what purpose. So I kind of had to go and learn that on the side first, and then when I was pretty well versed in that, I came back and the docs made more sense. But this is what I want to give you a shortcut through in this talk today. So I want to explain the basic concepts, the fundamentals of cryptography. But in order to keep it practical, we'll actually see code examples from the crypto module of how to actually do it with Node.js and JavaScript. So let's get started. My name is Yonatan Mevorach. I'm from Wix.com. I work in their DevTools group, which build developer tooling. And this is where you can find me online. So the first thing that comes to mind when we talk about cryptography is encryption, okay? And encryption is this process where two parties, people, computers, can exchange information over a channel which is inherently insecure and still be satisfied that the meaning behind their correspondence isn't known to anyone else. And typically, we talk about these characters, Alice and Bob, when we give cryptography examples, and also Eve, who is a malicious actor who is trying to decipher their secret communication. By the way, Alice and Bob are at the conference today. Luckily, Eve is not here, so no need to worry. And basically, for this first type of encryption, we have this thing that must be kept secure and known only to Alice and Bob, which is the key. Now, the key is just a piece of data. And the security of the encryption comes from the fact that only Alice and Bob and no one else knows the value of the key. And we'll talk about how they decide on the key and share the key later. So let's start with kind of a mental model of how encryption works and define some of the terms. So first, we have plain text, which is the original message that they want to share. And we have the key itself. And Alice applies some encryption algorithm, and she gets the ciphertext. The ciphertext is the encrypted message. For example, if the message is heapcon, the ciphertext looks like some random value. And then even if this is shared over a channel where Eve can review it, there's still nothing bad happens. And in order to perform the decryption, the reverse to the encryption, Bob uses his key and applies the decryption process, and he gets back the original message. So if we want to do this in real life, we need to add some more, complicate it a little bit. The first thing that we need to decide on is specifically which encryption algorithm to use, because there are many, as we'll see in a minute. But basically, all of these work by performing these set of transformation and substitution on the original plaintext and the key as well. So this is the first bit of code from the crypto module, which I'm showing here today. This is the getCipher function, and as the name suggests, this returns a list of all of the ciphers or the encryption or cryptography algorithms that are available on your machine. So for example, on my machine, this returns 171 different algorithms that I can use. So in our example for encryption, we're going to talk about a type of AES encryption. This is a family of algorithms that are called that because it's an advanced encryption standard. And as the name suggests, it's a standard, so it's widely implemented in several languages and systems. So you can use one language for the encryption and send it to another system in another language and do the decryption. And it's advanced and considered safe to use in today's systems. Specifically, we're going to take a look at AES 256. This is the size of the key which we're going to use. And the longer the key is, the harder it is for someone like Eve to try to brute force and guess the key, which makes the encryption more secure. And we're going to use CBC mode. CBC stands for cipher block chaining. And this is a mode of encryption where we first split the plaintext into these blocks, and we encrypt each one individually. Now, in order to compute the first block, we need to pass in something which is called an initialization vector, which is going to make our encryption more secure, and we'll see why right now. So this is how the process works. We have the plaintext and the key. Now we also have the IV. The value that we use as the IV is just a random value. So that means that even if Alice sends the same message to Bob every morning, she greets him with hello, she will use a different value as the IV every time. And because the encryption process is deterministic, now it has a different input value every time. So that means that the output that we'll get will be different every time. And this will make things harder for Eve to try to find patterns in the encryption and break it, because every time there's a new message, it's a bit different. So now Alice sends Bob the IV, the ciphertext, and the algorithm, or they can just decide that they always use the same algorithm, so it doesn't have to be part of the message. And then Bob is able to insert the output from Alice, and he will get the original message. So let's see how this is done in code. This is Alice's part to perform the encryption. So first she chooses the algorithm to use, one of the values returned by getCiphers. And then she needs to convert the plaintext message into a buffer. We never work with strings directly. We convert them first into a buffer, and then we use them. In order to get a random value as the IV, she can use the random bytes function from the crypto module as well. She loads the key into memory. We'll talk more about how we decide on what the key is. And then she can call create cipher IV, passing in the algorithm, the key, and the IV. This gives her a cipher object to which you need to pass the plaintext. You can do this if you're composing the ciphertext over time with input that's coming in gradually. You can call it multiple times. But then in the end, you call final, and that's how you get the final ciphertext. To perform the decryption, notice how much this API is kind of the reverse mirror image of what Alice is doing. So this is Bob's decipher code. He gets the IV, the ciphertext, and the algorithm. He loads the key into memory. He calls create decipher IV. Very similar looking, update, final, but this time what he's getting back is the original plaintext. So this is how the encryption works. So we talked about the key. We mentioned that this is the thing that's actually making our encryption secure. If the key is not strong enough, then the encryption won't be worth anything. So let's talk about how we decide on the key. Now, we might be tempted to use a human memorable password as the key, and we might think we're being clever by replacing like O's with zeros and all these kind of games. But if we do that, if we use the password that we can remember as the key, we're making life very easy for Eve, the attacker. Because we mentioned before that the size of the key is 256 bits, this represents a large number of options. If Eve can guess that we're lazy and we're using a human memorable password as the key, then she doesn't have to try all these combinations, and she can try to brute force and loop through a much narrower set of options. So we need to not use a password as a human memorable password as the key. But what can we do if we still want to base some password that we can remember as the basis of our key? So this is what we can use, something which is called a key derivation function, or KDF for short. And what this will allow us to do is it's a deterministic function, just like a hash function, which you might be familiar with from computing the integrity of a file. So given the same input, it will always return the same output. But interestingly, normal functions, normal hash functions, any function that you can think of, it will be better if it will be as fast as possible. But KDFs are actually designed to be slow on purpose, slow by design, both in terms of memory and CPU. Why is this? This is because we want it for Eve, if she's trying to, if she goes online and finds a list of the 10,000 most used passwords, and she wants to try to use this as your key, she will try to run this costly function as many times as the input she's trying, and looping over all these options and executing this expensive function will take her a long time. So this is why we do this. But if you think about it, Eve doesn't have to try to do this. She can go online and find the list of the most used passwords, compute the KDF value for each one, perform this only once, and she can keep this and then try to break the encryption later. Or she can go online and find somebody who already did this and just find the keys. And then the KDF only made our encryption process more complex, but it didn't add anything to our security. So this is why in the real world, the KDFs have another input, which is the salt. The salt, similar to the IV that we saw before, is a random value. And because this random value is part of the input, even if Eve has the salt, she will still need to perform the expensive calculation of trying each password with our unique salt, and this will take her a long time, hopefully longer than it would take for it to be worthwhile for the attacker. So those are KDFs. Let's see how this is done in code. We have 3 KDFs baked into crypto module. This one is called scrypt, secure crypt. And basically, you get the password. You generate, again, with random bytes, the salt, and you pass that to the scrypt function, and you get back the key that you can later use. So as we saw, being able to compute and use random values is super critical when we're doing cryptography. So let's talk about how you do that securely. The first thing that you need to know is avoid the urge to use what you already probably know if you're a JavaScript developer, which is math.random, because it is not considered cryptographically secure, which means that the attacker can either influence what this will return on your machine, or they can guess what this will return on your machine, and then this introduces a big risk to your encryption. So what do you use instead? We have several ways of generating random values inside the crypto module. All of these are asynchronous, but they have like the callback syntax. So if you want to use them with promises with await, you need to call util.promisify on them first. So the first one is random bytes. We showed this before. You give it the length of the buffer that you want to get back, and it returns a new buffer with that size with random data inside. You have random fill, which takes an existing buffer and fills it with random data. You have random int, which given a range returns an integer within that range. And you have random UUID. OK, so as we talked about before, the fact that Alice and Bob exchanged this key and it's only known to them is what makes our encryption secure. But if Alice and Bob represent computers and they're on other sides of the world, how can they establish this key to begin with in an offline manner where Eve is not able to see the key? So this is a pretty big problem. And this is something that Alice thought long and hard about. And to be honest, I thought long about this as well. And this was something that was difficult for many people who were trying to solve this problem basically for centuries. And this became known as the key distribution problem. Now, in the 1970s, a group of scientists came up with a solution to this problem. So let's see their solution to this problem. Their names was Diffie-Hellman, and the algorithm, which is called the Diffie-Hellman key exchange, is named after them. It's quite complex. Don't worry if you didn't get all of it. What's more important is what they get at the end of the process and how it helps avoid the key distribution problem. Okay? So Alice needs to have 3 values, the prime, the generator, and a private key that she keeps private. And using that, she yields her public key. She can send over this to Bob. Bob does the same process with his private key, which gives him his public key. Then with Alice's public key, he gets this value, which is the shared key. Then he sends his public key back to Alice, and using Bob's public key, what Alice does is she arrives at the exact same value. So don't worry about all the values, but the interesting part, the thing that solved this key distribution problem after such a long time that people found this problem difficult, was that even though Alice and Bob communicate in the open, even though Eve managed to see all the correspondence between them, only Alice and Bob ended up with this value in purple, and then they can use this as the key. So this was a huge achievement. But this still has some issues. Wait, first I wanted to show you, how to do this with JavaScript, right? So the first thing that Alice needs to do is to perform the key exchange is called create Diffie-Hellman. By the way, this is quite slow. On my machine, this takes like 20 seconds. And then she's able to get the prime, the generator, and the public key. And then when Bob gets the prime, the generator, and the public key, he can calculate his public key. And then you can also already see the secret key. And then Alice receives Bob's public key, and she's able to get the secret key as well. So as you can see, this works rather well, but you have to do this dance where they send the key back and forth before they can even start the encryption. So this is where there's room for improvement. Luckily, there's another group also in the 70s, also in the US, a group of researchers who came up with another solution to the key distribution problem around the same time. And the algorithm, which is widely used today, is known after them. This is the RSA method. So let's see how this completely avoids the key distribution or the key exchange by the fact that you use different keys for encryption and decryption, and this is why we call this asymmetric encryption. So Bob now has 2 keys, a private key and a public key. As the name suggests, he keeps the private key private and the public key is made available to anyone. And then if Alice wants to send Bob a message, no need to first exchange keys. She can just find Bob's public key and encrypt the plaintext with the public key, send Bob the ciphertext, and then using his private key, Bob can encrypt. So only someone with access to Bob's private key can decrypt a message that was encrypted by anyone using the public key. Let's see how this is done in Node.js. First, to generate the key pair, and keep in mind that Bob only has to do this once, not just for communication with Alice, but for communication with anyone. So you can call the generate key pair, and this will already have the 2 keys there. You can call .public key and export it to a file, and .private key and export it to a file. Now, if Alice wants to send a message to Bob, she can read his public key into memory and convert the plaintext to a buffer and call public encrypt in order to get the ciphertext. She needs to pass in the key, the plaintext, and this configuration value, that she needs to choose, called the padding. And then to perform the decryption, Bob gets the ciphertext. He reads his private key into memory, and then he can compute the plaintext using the same parameters. And that's how he gets the original message. So we might be tempted to think that this is it. The problem of cryptography is now completely solved. But let's think about where we still have some things that need solving. So one of the things is the fact that now anybody in the world can send Bob an encrypted message, but how can Bob know that the message really came from a certain entity that they expect? Well, this is where we get into the process of signing and verifying. So let's take this example where Alice is one of the organizers of HeapCon, and she wants to send Bob a message that he can go into the conference. This is like his ticket or his free ticket. So Bob needs to be able to prove, first to himself, but then also to anyone else, that the message really came from Alice, because otherwise it has no value. So in this example, we're going to talk about the fact that the message is not encrypted. The message can be visible by anyone. You can combine this with encryption if you want. So in order to sign this, give this proof that the message really came from Alice, Alice uses her private key, which only she has a copy of. And she uses the message, and she gets this signature value. Then she sends Bob the message and the signature. Her public key is available to anyone. And then Bob can perform the cryptographic verification on this. He takes Alice's public key, the message, and the signature, and performs a verification algorithm. And this will only return true if the signature came from someone with access to Alice's private key. And this is why this proves that the message really came from her. So let's see how this is done in code. So to perform the signing, Alice first reads her private key into memory. She takes the message that she wants to send, and she calls crypto.sign. And then she needs to pass in the hash function to use as part of the signing process, the message, and the private key. And then to perform the verification, what Bob has to do is get the message, the signature, read Alice's public key into memory, and call crypto.verify, passing in the same parameters. And this will return either true or false, based on if the math and the cryptography all line up or not. Now, I want to take a slight detour here and ask, when do we ever get to use this stuff? Because, as you can imagine, this is like the basis behind other things that are already working for us that we hardly need to touch day to day, like SSL and HTTPS. But when do we get to develop an application based on cryptography? So I want to give this example. I'm not sure how this was here in Serbia, but where I'm from 3 years ago, in order to go into a coffee shop, you had to perform this fake ritual with the host, where you would show them this QR code that proves that you are vaccinated. Now, they never actually bothered to scan it, so it was completely meaningless, because it could have been just a link to a Rickroll video. But actually, behind the scenes, there was, if it was actually used correctly, there was a good solution there. What the QR code contained was actually not encrypted. It was a plain text, details about you, what's your name, when were you vaccinated, and a signature that was signed with the private key of the Ministry of Health in your location. And the public key was really public. It was available on GitHub for everyone to download. So you could either use the app that the Ministry of Health provided, or you could create your own if you don't trust it, that in a completely offline manner validates that the person showing you the certificate really was vaccinated on this date. So now we're back to thinking, is cryptography solved? Did we solve all of the problems that are out there? So we talked about the encryption, the key distribution problem, and how we can verify that the message really came from someone. So in what I showed before with Bob verifying that the message really came from Alice, if you think about it, Bob doesn't really know for sure that the message really came from Alice. All that he knows is that he has this signature that matches some private key that somebody has private, and that person is claiming to be Alice. How can he know for sure that he's talking to Alice specifically? So this is where we get into public key certificates. These are certificates that prove that somebody, a specific entity, is the owner of a specific private public key. So what I like about this is the fact that really there's no magic solution here. There's no smart revolutionary algorithm like we have with the key distribution problem. Basically, it's the same as in real life. In order for Bob to trust Alice, he needs to first trust a third party that knows them both and will kind of introduce them. So in this case, as I'm sure you can see from the close, Carol is Bob's sister, and she's always also a friend of Alice, and she will help establish trust between them. So what Alice will now do is create a certificate that proves that she's the owner of her public key, and anybody who already trusts Carol will be able to trust this certificate. So in order to create the certificate, Alice will take her public key, which is the thing that she wants to establish ownership of, and add some metadata like her name, her country, etc., and create something called a certificate signing request with the TBS. TBS stands for to be signed, and she provides this to Carol. And then Carol and Alice talk in however way they want, and if Carol decides that she wants to vouch for Alice, then she will use her private key to create a signature, similar to the process we showed before, and this signature will be part of Alice's certificate. And then Bob, because he already knows and trusts Carol's public key, he will be able to verify the signature on Alice's certificate using the same process we showed before. And if all the math and the cryptography lines up, he knows, OK, this is for sure was signed by Carol, and I trust Carol, therefore I will now trust Alice as well. So let's see how this is done in Node.js. We have a class called the X509 certificate. X509 is the name of the RFC, or the standard for how certificates are structured. So he reads the certificate file into memory. And then he can read metadata on the certificate, like who is the subject, who is the certificate for, Alice. CN stands for common name. Who is the issuer, Carol. What is the validity period of this certificate? And crucially, to perform the verification, which is it's important to take time and do, he can read Carol's Carol's certificate into memory. The Carol certificate contains Carol's public key, which is used to verify Alice's certificate. And if this returns true, now Bob can trust Alice's certificate as well. Now, you might be asking yourself, if you're always looking for like holes in what I'm saying, and I hope you are, how come Bob trusts Carol to begin with? Well, how come you trust your sister? Well, the answer is obvious. You need to first trust your mother, and so on and so forth. So if in the world of certificates, we talk about certificate chains. You can see this in your browser if you look the information of your certificate. You can go through these hops where you want to trust a new certificate. For it, you need to trust a new certificate, so you go to the certificate above it, until the end, when you reach the mom certificate, where this is a certificate that is just baked into your browser. You don't validate it with another certificate, so you just trust it, and this establishes trust for the whole hierarchy or for the whole chain. So we've covered all of these cryptography fundamentals, and I hope this helped provide you with some knowledge about this field. If you want to find all the code I showed in the talk today, all of the code is here, and it's also structured as unit tests, so you can run them and make sure that they passed, because we're talking about cryptography where we don't trust anyone, so don't trust me as well. Run the code examples. This is where you can find me online. I write about cryptography. I also write about silly projects like tearing out the parts of an arcade machine and turning it into a Grafana monitor. So if that sort of geekiness interests you, you can find that here. And thank you for inviting me if you have any questions. Thank you.
Thank you, Yonatan. Any questions?
It's okay.
Please, if you have, raise your hands and volunteers will come.
I never ask questions well. I'm too shy, so I understand where you're coming from.
Yeah, if you're too shy, you can always ask through the Huva app, and you can answer later. And please, if you have any questions, please approach Yonatan after in the venue and ask him any questions you have. If no questions, that's it. We have a pause here, and we'll be back again at 11:45. Thank you all.